thanks for this impressive presentation. It is so exciting presentation. I think we could listen to you for hours. But okay, now it's time for discussion and question. So we have many questions from now, and I will try to do my best to ask most or all of them. So first, we had a very interesting question from Travis Warnis. Have you investigated using optically clear anvil materials such as you know, aluminum oxynitride alon? Could measuring the interface between the sample and rear anvil increase measurement fidelity?
No, we have not done that. I think that's a very interesting suggestion. I think this is really fascinating. And, you know, that is something which we have not done. You know, we have spent most of our time, as I mentioned, just developing the technique. I think there are many promising avenues like the one mentioned that, you know, we should be pursuing. Thank you for that suggestion.
Also a question from Christophe Charnota. Hello, Ravi. Normal and shear waves are steady in these experiments. What do you answer? Are
these easy experiments, he's asking?
Steady, are normal and shear waves
steady? Yes. So that's an excellent question, Christophe. I mean, you know, this is something which I didn't have the time to go into the details. You know, as you know very well, you know, you're an expert on the subject, is that when the shock waves propagate through the material, and these shock waves, the normal waves are steady because, you know, it has essentially enough time using the Planck criterion to develop into a steady shock. But the shear waves are propagating into this already shocked material, and so they do undergo dispersion. And this is why we need to use this numerical simulations to be able to extract this behavior, because that will the numerical simulations account for this dispersion. So you want ideally what you want to know is the interface condition, what's going on there. So one has to do an inverse analysis essentially from the free surface velocity to what's happening at the interface. And you know, that is something which Rod Clifton has been working on, but we do use direct numerical analysis to infer the interface conditions and to be able to get the strain rate and the stress and so on. Thank you for that excellent question.
Yeah. Thank you. Another question from Brian Burke, who is asking what are the specific limitations of the models that were used. So of course we know the limitation of the Johnson model, but maybe we are dealing with other models.
Yes, so one of the things, you know, most models don't account for the pressure. You know, the Steinberg-Guinan model is one of them. As we know that these are all of them are phenomenological models. So we need to be able to develop models which are probably mechanistic based models, and that is something which we are lacking now. And one of the things, that's one of the reasons, you know, we wanted to do these molecular dynamic simulations, is to be able to understand what are the mechanisms. You know, what are the origins of this pressure dependence. So the Steinberg-Guinan model is an excellent model because it accounts for the various dependencies, but obviously the constants and the dependencies are not well known. So one needs to develop sort of multi-scale models. And also the other thing is that, as I mentioned in the case of magnesium very briefly, is the anisotropy which develops. And you know, we are using isotropic models, and that's one of the limitations.
Mm-hmm. Okay. I'm not sure with a question from Santosh Yadav asking, is the diffraction grating used during the actual test the same as used in the calibration tests? I suppose it is. And does it create any issue with the measured value upon reuse using them?
No. So that's a great question in the sense that, you know, we use the same diffraction grating. Because the diffraction gratings create this very sharp diffraction orders, which we can use. So this is just a measurement technique, which doesn't interfere with the material behavior itself. So we use the same parameters. But obviously, we can change the sensitivity of the grating if we wish.
Okay. Also, I have two questions from anonymous audience. But in the same kind of interest, what is the uncertainty on the measurement of the transversal velocity? And second one is it very challenging? It's very challenging to get repeatable results even in SHPB tests. So what precautions are necessary to ensure repeatability in these complex experiments? What level of squatter in the experiments are permissible?
Yes. So, there's again a great question. Uncertainty is also very important to characterize. And, to answer the first question, we can measure transverse velocities within about 0.5 to 1/2 to 1 meter per second. So that's the resolution of the transverse velocity measurements. So we can go up to like 0.5 meter per second or so because of the fringe constants which we use using the diffraction grating. And the second question is like the repeatability of the experiments. One of the things which we have done, again I didn't have the time to show, is to use different angles. Okay, in the case of when we use tungsten carbide or steel angles, especially at low pressures, we can validate whether we get the same response by using this procedure. So we have done that. And in one of the plots, I showed you the scatter in the measurements. So there are some uncertainties associated with this. And of course, it took us quite a while to stand up this experiment. But now, even though the experiment is described as complex, now we do these experiments routinely on, we are beginning to get good results, and these are doable experiments.
Okay, another nice question from Cyril Bollis. I was asking the same question. Is there any friction at the interfaces with the sample and the anvils? Does it affect the results? And I would add also how the sandwich is prepared. Are there any sticking between the front anvil, the samples, and rear anvil?
Yes.
Or are they just in contact?
Yeah, so these are great questions. These are basically contacts. So because these things, the samples and the anvils, they're lapped extremely flat. So within like wavelengths of light, right? And then once they're lapped, they're just held together, and it's glued at the edges of the sample. And the interface is like essentially perfect contact. And with the perfect contact, when we talk about the friction, one of the things is which we worry about is the slip. So there shouldn't be any slip. If there is slip, we will immediately observe in the transverse response, even though this won't show up in the normal response. In the transverse response, we will completely lose the free surface velocity. So that's how we know the slip has occurred. So in the sense that this is nearly perfectly bonded, so that means there is no slip at the interface. It's perfectly bonded, one can assume. But obviously friction is a much more complicated case. Again, I didn't show you the results of the failed experiments. So that is why as we go to higher pressures, we lower the angle of the obliquity angle. So we go to smaller and smaller angles so that everything is perfectly sticky.
Okay. Okay, another question from Justin Brown. Does your new method still require the anvil to be stronger than the sample? I wonder if the use of a simple metal for the anvil could simplify or increase the fidelity of that calibration.
Yeah, so that's a great question. Is that one of the things which we have done is, as I told you, we have gone to metal anvils. Like in the case of magnesium, we used a metal anvil. Like we use steel anvils, tool steel anvils. So we haven't explored all the combinations, either experimentally or numerically. It is possible to go to this lower strength anvils, but that's going to be quite challenging, because the plasticity would then be dominated by the anvils. So in the case of going to tungsten carbide, and that's why copper is a good sample, is that there is a big mismatch in the strength. So we need to have hard anvils. Is always a very good idea. But the problem is, we may be running out of the anvil materials. So.
Mm-hmm. And another question from Tupanova Olga. asking what does the negative transverse velocity means in yes, with magnesium.
Yeah, so that's a great question. So this is essentially what it means is that the shearing is in the opposite direction. This occurs only initially. So because the shearing, you have some sense of the direction, either it can shear forward or backward. So this initially we could have small negative velocities because of the tilt. Because the tilt is very important. Because when you have the tilt, then your shearing starts certain way, but when the thing is closed, when the thing is completely closed, then you have this normal shearing direction. So that is just an artifact of the tilt, impact tilt.
Okay, and another question from the same people. Very interesting question. How do you get sure that HTV probes register the right signal corresponding to the transverse velocity? Yeah. And I have another question on the same topic. How important is the rugosity of the sample between the anvil, or how strict should it be? Does it affect the result at the interface?
Yeah. So these are again all great questions. So the HTV probes, they're extremely well aligned, because when you have the beauty of the diffraction grating is that you can't cheat, because the diffraction orders are fixed. It's governed by the Bragg condition, that you have this fixed angle coming out of the diffraction grating. So the probes have to be aligned. That's why the tilt is important. If there's too much tilt, then you won't get to collect the signals in the HTV probe. So it has very well aligned using a fixture in a 3D printed fixture, and only the signal coming from there could be collected. And also the diffraction orders are discrete, so you have the signal. And I think the other question is how well the sample interfaces are, and this is very, very important to have very flat samples and parallel samples, and this is done by using lapping. And so we take extreme care, and a lot of time is spent really just assembling the targets, and this is an art.
Okay, and if we have question, Eric or Philippe, I will ask another question from Jérôme Mespoulet. How do you control, measure, or evaluate the angular error at the impact in these complex experiments? That's a question all experimentalists are asking.
Yeah. So this is again a great experimental question. Is that we have on which I didn't show you all the details of the sample, is that we have tilt pins at the impact phase. So that is how we measure the tilt. So as it impacts, it contacts the electrical pin shorting pins. So as they short the spins, then exact time of the contact at locations on the periphery of the sample. So from that we can evaluate the tilt, and so we know exactly the angle of tilt.
Okay, maybe we have time for one more question. One question from Anonymous saying, are these models available as inbuilt material behavior models in any commercial finite element codes like Abacus, the model you presented?
Yeah, this is Abacus. I think you need to be able to, some of them are available, obviously Johnson Cook and other kind of corpus Simons kind of things. So if you want to build your own thing, you can write, of course, in Abacus you can write UMATs and do the thing. And obviously codes like LS-DYNA, they have some of these models built in.
Okay. Okay, and maybe one last question. Okay, you are working with quite thin samples. I was asking me about each transfer between anvils and the samples. Are we staying in adiabatic conditions at the sample scale? What is your opinion?
Yeah, I think that's again a great question. So obviously, we are doing this experiments at high strain rates and also very short times. So the conditions are, more or less adiabatic. Obviously, how adiabatic is all relative, right? So because we have this, the excellent point the person who asked the question made was, this is a thin sample between very, this surrounded by this bulk tungsten carbide. So we assume that it's adiabatic, but this is something again we need to look at more using careful models in this time scales.
Okay, I think it's time to thank you again for this impressive and amazing presentation and for responding to all these numerous questions. So Eric, I'll let you conclude. Thank you.
Yes, thank you, Pascal. Can you hear me?
Yes.
Okay. Thank you very much, Ravi, for this great talk and for kindly accepting to share this moment with us. We got a lot of questions and interesting exchange, I think. So many thanks to each of you for your very strong participation. Thank you, Pascal, for this lively animation. And I would like also to warmly thank Philippe Viau for supervising the technical organization against all odds at a very inappropriate moment for him. So thank you, Philippe, I appreciate. We hope you like this webinar. In any case, we will be happy having your feedback on any aspects of the event, organization, communication, scientific value of the exchange. Our intention was to record this webinar. I don't know if we were successful, but if it is successful, the record will be available soon as a link on our website. So next month, we will have the honor to welcome another prestigious guest, Professor Katie Ramesh from Johns Hopkins University. He will talk on a mind-blowing topic, namely traumatic brain injury and the dynamics of the live human brain. So this webinar will be given on Wednesday, the 28th of April at 5:00 p.m. Paris time. And I invite you to have some more details on our website at www.dymat.org. If you haven't been receiving personally the invitation for today's webinar, please let us know and send us an email at inquiries@dymat.org, and you will be added to our mailing list. Another important reminder, our next international conference in Madrid will be organized in September, and it is open for registration. So I invite you to visit our website for more details. The next date on the agenda is the deadline for full paper submission by the 15th of April. And importantly, this date will coincide with the deadline for applying to DYMAT's PhD prize contest. So if you, your colleague or one of your students have been defending his or her doctoral research during the last 3 years, he or she would be eligible to applying to the contest. So we will offer a prize of 2,000 euros to the winner selected for the excellence of his or her PhD in dynamic behavior of materials and its applications. So again, I invite you to visit dymat.org website for more details. I think it's time to leave now. So see you hopefully on the 28th of April for our next webinar. Thank you again, and goodbye. See you soon.
Thank you, Ravi.
Thank you, Pascal. Thank you, Eric. Thank you, Philippe.